And now the time has come for quiz 11. We'll answer the problems. All right, here we go. Number 1. This is great. So we're in a brand new topic, which means that all the problems are just nice warm-up problems. Next week is going to be a lot more exciting. So find the integral of e to the 3x plus 1 over e to the x plus 1. Now there's a lot of things that people might attempt which are wrong, and things that, let me just say some crazy stuff. And see, one of the things that happens if you hang out with math teachers a lot, they'll say, oh my gosh, you won't believe the kind of craziness that my students would write on exams. So what are some things we would see which are wrong? Well, we'd be like, hey, there's a plus 1. We can cancel it, right? And then it's e to the 3x over e to the x, which would be e to the 2x, right? Right? No, of course not. That's nonsense. You would never, ever do that, because that would just make your calculus teacher very, very sad. So here's the thing. Integration, at its basic core, there's about 10 things that we can find the antiderivatives of. So when I say integration here, I'm really talking about finding antiderivatives of which I think we've explicitly written down maybe 8 of them so far. That list is basically the entire list of everything you're going to encounter. And so what we're going to do, really the goal here is always going to be, let's simplify to get it to something that we can integrate. Now looking at this, we say, okay, we see things like e to the x. So we know we can integrate, and in general I'll write it as e to the k times x, where k is some constant. And that would be 1 over k, e to the kx plus, of course, here's always a c. Now, our goal here is to say, well, can we take things that look like this and get it to something that looks like that? Now, it might be multiple somethings, and it's perfectly fine to have things being added and subtracted. So that's our goal, that's our thinking. So we say to ourselves, well, what can we do? Now, here's one thing that is often sort of hidden. That e to the 3x, how should we be thinking about that? Well, it turns out that e to the 3x, one way to think about that is as just a normal e to the x, that you cubed it. And why is that useful? Well, sometimes it can be useful because you can think of it as like, oh, it's something cubed. In fact, e to the x cubed, and the 1, turns out you can think of it as 1 cubed. So what you have is you have 2 cubes being added together. So this is going to be our algebra sort of side note. And a lot of our integration problems are going to boil down to saying, can you rewrite your integral using tools of algebra to get it to something that's easier to work with? So a cubed plus b cubed, in general, that's a plus b times a squared minus ab plus b squared. So if we use our algebra, that becomes, so this is our a, there's our b, so a plus b, e to the x plus 1, then a squared, so that's e to the x squared, minus a times b, so that's minus e to the x, plus 1 squared, which I'll write that as 1. Now divided by e to the x plus 1. Now, don't forget, you should always keep your dx. Why do you need that? Well, it's a notational thing for right now, but notation is going to become really important in future classes. So it's really important to sort of get into the habit of when it's not important, you do it, so that when it is important, you do it also. Now we see, aha, now instead of this crazy cancellation which makes no sense, we can cancel here. And the reason that you couldn't do cancellation here versus you could do it here is the fact that here it's addition. Addition doesn't really work well. But down here it's now multiplication, and that works splendidly. So what do we get? Well, now that that's been canceled, e to the x quantity squared, that's e to the 2x. And we have minus e to the x plus 1. You say, oh, okay, well, we have things being added and subtracted. That's actually great for us. We can break up and do integration over addition and subtraction, where we just think of it as little 3 separate pieces. So integral of e to the 2x dx minus the integral of e to the x dx, then plus the integral of, all right, as 1 dx. And now each piece is simple. Integral of e to the 2x, that's like k equals 2. So that would be 1/2 e to the 2x. Integral of e to the x, well, that's e to the x. That's a nice simple rule. Integral of 1, we didn't write that one down, but I think you might know that one. The integral of 1 is x. Good. And there we go, right? Right? Ah, right, good. Not yet. Plus c. Don't forget. So this is antiderivative or an indefinite integral. And every time you're doing one of those, you need to have a plus c. And if you forget a plus c, well, you're going to lose a point. And our goal is to get them all. Got to get them all. It's like the Pokemon. You know, want to get all the points. All right. Number 2. Find the integral x cubed plus 3 root x plus 5 all over x. Okay, well, again, we want to use our algebra here. Now, see this division, whenever you have division, you can put it under each individual term. Excuse me. So, this is the integral of x cubed over x plus, now 3 root x. I'm going to write that as 3x to the 1/2 over x and 5 over x. So now we just say, well, what is that? Well, x cubed over x is x squared. Here I have to the 1/2 upstairs to the 1 downstairs. So if I combine that, I would subtract the exponent. So this is really to the 1 power. 1/2 minus 1 would make this to the minus 1/2. Now 5 over x. Because it's 5 over x, we won't write that as 5 times x to the negative 1. We're going to leave it as 5 over x. Or really, I'm going to write this as 5 times 1 over x. Because 1 over x is its own little special case. And we wanted to handle that one in a separate way. So now we go through and say, okay, now we're going to think about doing it piecewise. At this stage, you could actually just go ahead and write the integral. I'm just going through just to sort of emphasize what's the thought process. So 3 is a constant, so that can actually come out. 3 integral x to the minus 1/2 and 5 integral 1 over x. So for the rule x to a power, you add 1 to the exponent. So that would be x cubed. Then you divide by that new exponent. So divide by 3 or multiply by 1/3. Then plus 3. Now add 1 to this exponent. Negative 1/2 plus 1 will be to the 1/2 power. And now we're going to divide by 1/2. So divide by 1/2 is the same as multiply by the reciprocal. So we're going to multiply by 2, which is 1 over 1/2. And then plus 5. Now this is the special case. You see, if it was x to negative 1, if I added 1 to the exponent, I'd get x to 0, and then I would have to divide by 0, which doesn't make any sense. But what does work here is the integral of 1 over x is log. Now, usually we write log x. Technically, it's log absolute value of x. Whatever makes you happy. If you want to be more technical, throw in the absolute value. If you just think log, we'll usually be okay with that. And of course, we want our plus c. And that's pretty much as simple as we can get. But I will point out that, of course, you have the 3 times 2. So that becomes 6. And x to 1/2, we can write that as square root of x. And 5 natural log of x. And there we go. Ah, that one's not so bad. Oh, these are great. These are fun. All right, good. So let's go to the next one. Find the integral of 1 over 1 plus sine theta. Now, looking at this, we say hey, that looks like trigonometry because, hey, that's trigonometry. Okay, so we're probably going to do some trig integrals. Now, the kind of trig integrals we can do, what are integrals we know the antiderivative for? Well, we can definitely do sine. We should mention that one because that's there, right? The integral of sine is negative cosine. We can do cosine. That's not so bad. Integral of cosine, positive sine. We can also, there's two more, do you remember? Secant squared is one. Do you remember what the integral of secant squared is? Tangent, all right. And the last one, secant tangent. Integral of secant tangent is secant. All right. So those are our four basic trig integrals. So probably our goal is take this expression, 1 over 1 plus sine theta, and make it look like some combination of these functions, sine, cosine, secant squared, secant tangent. So, looking at this, we say, what's our problem? Well, definitely, I don't like the fact that there's a plus sign down in the denominator. I want to get rid of that. In general, we love addition upstairs. Addition downstairs, that's just not our jam. We don't like that. So we want to get rid of it. Now, I don't just want to get rid of it by saying, aha, let me cover it up. I have to find a way using algebra, and in this case, trig identities, to get rid of that. So now we dig deep into our past and say, what are tools that we had that helps us get rid of things like a 1 plus sine theta? And of course, by saying get rid of it, we say rewrite it using more convenient notation. Well, one thing that we could try, and whenever you have a 1 plus something, it's not a bad idea to say, well, what would happen if I multiplied by a 1 minus something? Now, why do I bring that up? Well, one thing is, it's a tool we learned. This is multiplied by the conjugate. But another thing is it says, okay, if you multiply by 1 minus something, you're really making things squares. So sine theta, not a lot you can do with that. But sine squared, there's a lot of identities. At least there's one more, right? Because there's sine squared plus cosine squared equals 1. So if we apply this, what do we get? Well, upstairs, 1 minus sine theta, which is what it is. Downstairs, that's 1 minus sine squared theta. Now, what can you do with that? Well, like I said, there's an identity. What is another way to write 1 minus sine squared? Well, another way to write 1 minus sine squared is as cosine squared. Now, if you look at what we have, is we've traded it, so we have a lot more complicated stuff going on. If you compare the first expression to this current expression, it's definitely a more complicated expression. But notice what we've done. See, in the first expression, our plus was in the denominator. In our second, our plus, which now is masquerading as a minus, is in the numerator. And when you can put things into numerators, that gives you a lot of power because you can now break things up. So you have 1 over cosine squared minus sine over cosine squared. All right, good. Now is the time for us to say, okay, let's think about where our goal is. Our goal is we want to write it as some combination of sine, cosine, secant squared, and secant tangent. Because those are the things we can do. So we ask ourselves, for example, 1 over cosine squared. Is there a nice way for us to rewrite 1 over cosine squared? And how do we do it? Well, 1 over cosine squared is secant squared, right? Because 1 over cosine is secant. And now we're like, woohoo, victory! We have a secant squared. Nice! All right. Now, how about sine over cosine squared? Now you might be thinking, I know, can I replace cosine squared by 1 minus sine squared? No, that's going backwards. We don't want to do that. In particular, we love the fact that there's no addition and subtraction in the denominator. Don't introduce addition and subtraction unless you have no other option. So, okay, so let's not do that. So what can we do? Well, if we think about it, it's not looking like sine or cosine or secant squared, because it kind of, you might say, well, it's sine times secant squared. Well, the sine times secant squared isn't on our list. Multiplication, we don't know how to handle that yet. Let's think about this last expression, secant tangent. Now secant, what's that? That's 1 over cosine. Tangent is sine over cosine. So if we think about secant times tangent, that's really sine over cosine squared. So this last piece is secant tangent. In other words, it's on our list. So now both of our pieces are on our list. Life is good to us. So we say, okay, the integral of secant squared is tangent. And then minus the integral of secant times tangent is secant. And of course, plus c. Now, you might be asking, hey, why do you only have 1 plus c? Because didn't we do antiderivatives for both parts? And you could say, well, yeah, you could think of it as like every part has its own plus c. But the moral is, after you do that, you can combine the c's together. Because constants are like sponges. They absorb other constants. And so when there's multiple constants coming into play, you'll only end up with usually a single constant at the end. All right. And of course, well, we'll get there in a second. Number 4. Find the integral y minus 1 times y squared plus y plus 2 divided by y squared plus 1. Okay. Well, probably not too hard to figure out what to do, to start anyways. This is all algebra. So we want to say, let's figure out how to rewrite this using algebra. So one thing we can do is we can multiply out the top. So what do you do? Well, when you're doing multiplication like this, in other words, that's a polynomial times a polynomial, what you do is you're very patient, and you don't want to do foiling, right? Because foiling is first, outer, inner, last. Because there's also this sort of middle term. So, it would be like, well, the first, the mid-first, and so forth and so on. The Vermuffenlen. So, but let's think about the philosophy of foiling. The philosophy of foiling says, pick a term from the first part, pick a term from the second part, multiply them together, and do it in all possible ways. So, for example, y times y squared, that's y cubed. Y times y is y squared. Y times 2 is 2y. Minus 1 times y squared, minus y squared. Minus 1 times y, minus y. Minus 1 times 2, minus 2. All right. Good. dy. Now, we can do a little bit. See, I have a y squared there and a y squared there. That means that those two y squareds can cancel. That's nice. Good. You can also combine those together. So what do we have now? We get y cubed plus y minus 2 divided by y squared plus 1 dy. Now, our goal is to make it look like things we can integrate. Now, what are things we can integrate? Well, when we see that y squared plus 1, we know we can integrate something that looks like 1 over y squared plus 1 dy. That's a good one. Arctangent. What a beautiful, beautiful antiderivative. One of our best. And of course, other things we can integrate is if we have y to some power k, that's something we can integrate. That would be 1 over k plus 1, y to the power k plus 1. On a side note, you're probably not even thinking about this, but let's just point out that here we're integrating where y is the variable, and we're doing the same thing as if x is the variable. Is that okay? And why is it okay? And the answer is it's absolutely okay. See, we can have any symbol be our variable. The reason x is it's more tradition than anything. And so the more comfortable you are working with any variable, the better off you are. So anyways, our goal is to make things that look like those pieces there. So let's stare at this for a while. So y squared plus 1. The upstairs is way too crowded. We want to simplify. Now looking at this, I say, hey, y squared plus 1, y cubed plus y, they're very similar to each other. So see, suppose you didn't have that minus 2 there for a second. What can you see? Well, if you factor the y out on the top, what would be left would be y times y squared plus 1. And that's actually really good for us. So what we have is y times y squared plus 1 minus 2 over y squared plus 1. In general, one of the things you can think about when you're doing this is say, I have a y squared plus 1 downstairs. I want to make things that look like y squared plus 1 upstairs, because that can give me cancellation. So we now think this has two terms, y times y squared plus 1 over y squared plus 1, and then minus 2 over y squared plus 1. So again, taking advantage of our subtraction upstairs. The y squareds plus 1s now cancel. All right. So we have the integral of y, and I'll just do that integral, then minus 2 integral 1 over y squared plus 1. And now we have integrals we can actually do. The integral of y is 1/2 y squared minus 2. Integral of 1 over y squared plus 1 is arctangent of y. And then, of course, for good measure, and so that we make sure we get all our points, we tack on a plus c. And that's our answer. Good. All right. Wow. We're making good progress. Okay. Nice. So, here we go. Number 5. Find the integral of the absolute value of t dt. Ooh, now this is interesting. You see, why is this interesting? When we talk about derivatives, absolute value is sort of like our go-to, hey, it doesn't always have a derivative, because you know that if you remember what the absolute value function looks like, we can say that the absolute value function looks something like a v. And that has that little Sharpie corner, and right down here. It's like the sharp corner. And so there's no derivative. So what about antiderivative? And so here's the beautiful thing, is it will have an antiderivative, and because we're going to find one. Now you might say, how do you know we're going to find one? Because the problem tells us to. So that's how we know we're going to do it. In general, it turns out that as long as you have a nice continuous function, you'll always have an antiderivative. We don't actually know that yet. We will soon. It's coming. So, but all right. So how do we begin? Well, here's sort of a way to think about it. Is when we think about absolute value of t, the way for us to think about absolute value of t is we oftentimes think about it as a piecewise function. T if we're not negative, and negative t if we're not positive. Okay, so what can you do? Well, one of the things you can do is you can now take an antiderivative piecewise. So we could say, look, if we're going to take our antiderivative, we'll do it piecewise. So what would we have? Well, we would say, what's the antiderivative of t? So now I'll assume we're positive. It would be 1/2 t squared. All right? And that's if we were greater than or equal to 0. What's the antiderivative of negative t? Well, minus 1/2 t squared. And that would be if we're less than or equal to 0. Now, the only thing that we really want to make sure happens is that they agree at 0. Well, at 0, they're both 0, so that's good. So there's an antiderivative, and then always, of course, there's a plus c. So this right now is just some function plus a constant. And this has the property that if you take the derivative, lo and behold, the derivative for greater than or equal to 0 is t, derivative for less than or equal to 0 is negative t, and at 0 they both agree, and therefore it is the right derivative. in some sense we could say this is our answer, and it really is our answer, but it's not elegant. And so we'd like it to be slightly more elegant. So how can we make it more elegant? Well, it's piecewise and it looks a lot like this. We say, well, can I somehow take this sort of expression, make it look something like that expression? It's very close already. See how these pieces are almost the same except for the negative sign. One of them is greater than equal to 0, one of them is less than equal to 0. So one thing we could do is we could say, well, the difference here is a factor of a half t. So let's take that factor of a half t out. So half t, and then there's sort of these two cases. It'll be t if we're greater than or equal to 0, and negative t if we're less than or equal to 0. And then, of course, add on your constant c. And now we say, hey, this part is familiar because it's exactly that. That's absolute value of t. So we get 1/2 t, absolute value of t, and then plus a constant c. And there's our antiderivative. And that's it. That's it. So it's not meant to be hard. I mean, there's sort of a couple ideas here. If you have a piecewise function, to find the antiderivative of each piece, make sure they line up wherever you glue them together, and then you're good to go. And of course, the other thing is, hey, things which don't have derivatives can have antiderivatives. So they're not exactly the same thing. So you got to be comfortable with that. All right, that's number 5. It means we're halfway through. Doing great. All right, let's do number 6. So suppose that the second derivative with respect to t is 2 minus sine of pi t, and that we know where we're at time 0, we're at negative 2, and at time 2, we're at 5. What's the derivative at 1? Okay. Interesting. Interesting. All right. Well, so let's start. We know we have y double prime of t. So I'll write that down. 2 minus sine of pi t. So we want to get to y prime of 1. All right. Well, if I want y double prime, if I have y double prime and I want y prime, what do? I integrate. All right. So let's integrate. So y prime of t, well, integral of 2, it is 2t, right? So we're taking antiderivatives here. All right. How about the integral of sine of pi t? Well, okay. So integral of sine of just some constant k times t. Now, normally the integral of sine would be negative cosine. So it's still almost like negative cosine. The only thing that we have to do, and there's always a constant c on the end, is you have to account for the fact that there's a k on the inside. And you do it by multiplying by 1 over k out front. So here we have a minus sign. So because of that other minus, that'll become a plus. The k is pi, so there's a 1 over pi. And then there's a cosine of pi times t. Cool. Now, at this point, what else do we need to say? Well, we do need to say one thing. There's a plus c. All right. Well, we're basically done, right? Because we need y prime of 1. So, lo and behold, that tells us that y prime of 1 is equal to, plug in 1, you get 2 plus 1 over pi cosine of pi plus c. Well, cosine of pi is negative 1, so that's 2 minus 1 over pi plus c, right? Right? And that must be the answer. We can circle it, can't we? See, I'll put a box on it. Is that the answer? No. What's wrong? Why is that not our answer? Well, the problem is we have a constant here. And we don't know what our constant is. And depending upon what our value for c is, it's a different value, a different answer. You see, essentially right now we're just saying y prime 1 is some number. that's not enough. We really need to know c. So we say, okay, well, how do we recover c? Well, we say, let's use information. So that's why you have this additional information given. Y of 0 equals negative 2, and y of 2 equals 5. Now our problem here is that these constants are not for y prime, they're for y. So I can't use that information here to solve for c, because I'm not in the right function. That means I have to go further up the ladder. Okay, so we're going to keep climbing our ladder. All right, so I want to get to y. So what is y of t? Well, that's to get from y prime to y, take the antiderivative. Antiderivative of 2t is t squared. All right, then we have a plus. We have a 1 over pi. Now, if we think about the integral cosine of kt, it's very similar. The integral of cosine is sine and plus c, but now you have to account for that k. So we're going to put another factor of 1 over k. So the 1 over pi is the constant, then there'll be a sine of pi t, and now I've got to account for that 1 over pi, so now there's a second 1 over pi. All right, now what's the integral of a constant c? The answer here is it's c times t. C is some number, so I'm thinking of c as a number. So if it was 5, the integral of 5 would be 5t. If it was 10, the integral of 10 would be 10t. Since it's c, the integral of c is ct. All right, are we done? They might be saying, don't you need a constant? And I say, well, that's a constant. Yeah, but don't you need another constant? And the answer is yes, you do need another constant. Every time you take an antiderivative, you need to introduce a constant. The fact that there was a constant here does not mean that we don't need to introduce a new constant. And this is a case where the constants don't combine. See, this constant has a t attached to it, and this one does not. So they have different behavior, so we can't just merge them into one single constant. All right, so now we have two things that we don't know, but that's okay because we have two pieces of information. Now our goal is to figure out what is c, because once we know what c is, then we're done. So let's start with 0, because usually 0 is our friend. Indeed, anytime you can get 0 involved in a problem, you should do it. So when we plug in 0, what do we get? Well, we're going to get 0 squared, well, that's 0. A bunch of 1 over pi's times sine of 0, well, that's 0. We're going to get c times 0, which is 0, and then we're going to get d. So y of 0 is d, but we know that d is negative 2, because y of 0 equals negative 2. All right, so that was actually pretty quick. Okay, cool. Now let's plug in 2. I suspect this one will be a little bit longer. Okay, so 2 squared is 4. We get 1 over pi times 1 over pi times sine of 2 pi. Sine of 2 pi is 0. All right, so that's still 0. Then we're going to get, plugging in t equals 2, 2 times c. Well, I don't know what c is yet, so 2c. And then we're going to get plus d. So plus negative 2, and that's all going to equal 5. All right, now what can we do? Well, we can move the constants across. And if we do that, we'll get 2 times c. Well, that would be, let's see, if I add 2, that would be 7. Subtract 4 would be 3. And, or we can say c is equal to 3/2. See, that was sort of our missing piece here. So now what we can do is we can say, hey, I just have to send that up into there. And now we can write down our answer. So we get that y prime of 1. See, the first part was fine. It's still 2 minus 1 over pi plus 3 over 2. Well, 2 and 3 over 2 are both, numbers. I can think of 2 as 4 over 2. So that would give us 4 over 2 plus 3 over 2 is 7 over 2 minus 1 over pi. And there you go. That's it. That's your answer. All right, let's do the next problem. Number 7. Given that f double prime of x is 6x plus 2, the tangent line to y equals f of x at x equals 2 passes through the origin, and the tangent line to y equals f of x at x equals 1 is horizontal, determine f of x. All right, well, what do we have? Let's just sort of say what we know. We want to find f of x, and we know f double prime of x, so we'll start by saying, here's f double prime of x. It's 6x plus 2. Now, if I want to get to f of x, and I have f double prime of x, I sort of want to step my way up. So, for instance, I can say, well, an intermediate step would be f prime of x. So, take the antiderivative of 6x plus 2. Antiderivative of 6x, well, you would add 1 to the power, so it would be x squared. And then you would divide by 1/2. Or sorry, multiply by half. Divide by 2. Right? And then the antiderivative of 2, well, it's 2x. And then, of course, plus a constant, c. So that's 3x squared plus 2x plus c. Now, that's f prime. How do I get f of x? Well, here, again, we keep stepping. Antiderivative of 3x squared. Well, 3 is constant. Add 1 to the power, x cubed, multiplied by the reciprocal. Plus 2, x, add 1 to the power becomes x squared, multiplied by the reciprocal. C will be cx, and then we introduce a new constant d. So that becomes x cubed plus x squared plus some constant cx plus some constant d. So that's what we have. So we're not done because we don't know what the function is, because c and d aren't yet determined. And of course, if you change c and d, you do change your function. So what do we need? Well, two constants say we need two pieces of information. So what are our two pieces of information? Well, here's one piece. The tangent line to y equals f of x at x equals 2 passes through the origin. All right, so that's one piece of information. And then the other piece of information is here, that the tangent line is horizontal. So two pieces of information, that'll help us solve for our two constants. In general, whenever you're doing a problem like this, every piece of information helps you get rid of one constant. Another way to think about it is I have 2 degrees of freedom, because every time I took an antiderivative, I got a new constant, which allows me to specify two things about what I want the function to do. And now we got to think about it. Now we could start in either order, but let's try to be smart. So let's think about what this involves. So the tangent line to y equals f of x at x equals 2 passes through the origin. So that means we take the tangent line at 2 and make sure it passes through the origin. The second one, the tangent line to y equals f of x at x equals 1 is horizontal. Now let's think about another way to phrase that one. What does it mean to say your tangent line is horizontal? Well, horizontal means it's flat, right? How do you know if your tangent line is horizontal? Well, tangent line horizontal means that the derivative is equal to 0. Because horizontal means that your slope is 0. You're not rising or running. And we're at x equals 1. So we know that the derivative at 1 needs to equal 0. Okay, so what we can do is we say that's one of our conditions. So if we come here, we can say, hey, f prime of 1 would be equal to 3, then minus 2, and then we have plus c, and that has to equal 0. So what does that say? Or c has to equal minus 1. Yes? All right. Just checking my notes here. That does not seem to be the right answer. Aha! 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 That's... Ah! I can't believe I screwed that up. See, this should be 3 plus 2 plus c. Ah! Why did I put a minus 2? I can't believe I did that. That's silly. That's silly. That was for some reason I was plugging in a -1, not +1. Oh my gosh. I can't believe it. I can't believe it. Whoops. Ha! -5. Okay, alright. Okay, alright, Steve. Slow down. Slow down. You know, you don't want to make too many more errors. Okay, anyways. Okay, so c equals -5. Woohoo! Alright, so we can update. Now we have x cubed plus x squared minus 5x plus an unknown. Alright, we're a little bit closer. A little bit closer. Okay. Now, let's use our other condition. The tangent line to y equals f of x at x equals 2 passes through the origin. Alright, cool. So what does that say? Well, let's remember our tangent line. So, in general, if we have a function f of x, we have that the tangent line looks like what? So the tangent line is y equals f at a plus f prime of a times x minus a. That's just the generic formula. So that's f prime of a times x plus f of a minus a f prime of a. So this part right here is your y-intercept. If we're passing through the origin, that tells us that we want our y-intercept to be 0, because that's where the origin is at. So we need the following to be true. We need that the function at 2 minus 2 f prime of 2 has to equal 0. So let's plug in 2. We're going to get 8 plus 4 minus 10 plus d. Minus 2, plug in to f prime of 2. So that would be 12 plus 4 plus c, but we now know that c is minus 5, and that has to equal 0. Alright, I'm noticing that my d is looking awful lot like my 0, so I got to be careful when I read this. 8 plus 4 minus 10, that's 2. 12 minus 10 is 2. So 2 plus d, then minus 2 times, I'll have 12 plus 4 is 16, minus 5 is 11, equals 0. So that's minus 22 plus 2, so we get d minus 20 equals 0, or d equals 20. So we end up with x cubed plus x squared minus 5x plus 20. And that's our function. That's the one we were looking for. Woohoo! We found it! Success! Or, as they say in Klingon, kapla! Which is, of course, Klingon for success. Alright. Number 8. Approximate the area under the curve y equals x squared minus 3x plus 5 from x equals 0 to x equals 4 using a Riemann sum with 4 equally spaced intervals and using the right endpoint of each interval. So what I'm going to do is I'm not going to sketch the function, because I really don't need to know the function. I know I'm going from 0 to 4, and I'm going to split this up into 4 equally spaced intervals. So that says I want to split from 0 to 4 into 4 equal parts. I'll go halfway and then go halfway again. And it looks like we are really nice. 0, 1, 2, 3, 4. Okay, that's good. Now, what do we need? We need the right endpoint. So that says for each interval, we're going to go to the right-hand side. And we're going to use that function. Now, the last thing we need to know before we really start is what's our width? Now, another way to say the width is what's this, or we sometimes call that our delta x. And in this case, because they're equally sized, they're all 1. So what we're going to have is, if we think about this as, this is our function here, this is our f of x, then what we get is that the area is approximately, well, for the first interval, we're going to take the function at 1 times the width of the interval. For the second interval, we take the function at 2 times the width of the interval. For the third interval, we take the function at 3 times the width of the interval. And for the last interval, we take the function at 4 times the width of the interval. So now we need to evaluate. So function at 1, we get 1 minus 3 plus 5. I think we can do that one. That would be 3 times 1. Well, that turns out to be 3. We'll do that in our next line. Okay, well, they're probably going to get more challenging as we go. All right, that's f of 2. 4 minus 6 plus 5. So the 4 plus 5 is 9. Minus 6 is, again, oh, it's 3. Okay, we already 3 this problem. The function at 3. We're going to get 3 squared minus 3 times 3, so that's easy. Those knock out, plus 5, so that's 5. Function at 4. 4 squared is 16. 3 times 4 is 12. 16 minus 12 is 4, plus 5 gives us another 9. So we have 3 plus 3, which is 6, plus 5. That gets us to 11, plus 9 gets us to 20. And that is our approximation using a Riemann sum. So these kinds of questions are actually not so bad. You just have to know, all right, what's the width? Don't forget to check the width. Break up, figure out your intervals, and figure out which point you're using for each interval. And then just work it through. Because remember, a Riemann sum, that's really, it's just a sum from, well, your first interval to your nth interval. So this is the first, second, third, fourth. You take your function at some point on that interval times the width of the interval. And so these aren't hard problems. Once you get the hang of it, you'll fly through them. And, well, I suspect we have a couple more, and so we'll probably fly through those as well. One could hope, right? Number 9. Use a Riemann sum to approximate the area under the curve y equals 20x over 1 plus x squared from x equals 1 to 4 by using a partition with 3 equal width parts. And now we're left hand. Okay, so again, I really don't need to draw the function. I just want to understand where I'm going. I'm going from 1 to 4. I'm going to break this into 3 equal parts. Now, if I go from 1 to 4, where are my dividing lines? Now, hopefully you can sort of see what this should be. Now, if you're not sure, let's think about how far 1 and 4 are away from each other. Well, they're 3 apart. And we have 3 equal widths. So we take 3 divided by 3 means that the width of each part needs to be 1. So we'll just make that note here. Delta x equals 1. Now, to figure out the points, well, you say, okay, start at 1 and go 1 on each step. So 1, go over 1 gets us to 2. 2 go over 1 gets us to 3. 3 goes over 1 gets us to 4. And now we've done our job. And for each interval, we need to figure out which point we're using. Well, that is going to be told to us. So we're going to choose the left. So we're going to choose those points. So now, and of course, this is our function f of x. We're ready to go. So what do we get? Well, we get that the area will be approximately, and remember, Riemann sums are approximations, so that's okay. So for the first interval, it'll be the function on the left end, which is 1, times the width, which is 1. For the second interval, function on the left end, which is 2, times the width of the interval, which is 1. And then for the third one, the function at 3 times the width, which is 1. We only have 3 terms because we're doing it with 3 parts. Now, I will say, you probably think, wow, is it always going to be 1? Well, it will often be 1 for problems that we do because we need to do things which are computationally straightforward. So 1, sometimes it's 2, sometimes it's a half, but we're not going to do very many parts because anything that requires hand computation, we don't want to have many parts. All right, so function at 1. So we plug in 1. We get 20 times 1, which is 20. Downstairs we get 1 plus 1 squared, which is 2. Function at 2. 20 times 2, which is 40. Downstairs we get 1 plus 2 squared, well, that's 4. We'll clean that up in a second. Function at 3, well, that would be 20 times 3 upstairs is 60. Downstairs we get 1 plus 3 squared. That's 1 plus 9. We'll clean that up in a second. So 20 over 2, all right, that's 10. 40 over 5, well, that's 8. 60 over 10 is 6. And 10 plus 8 plus 6 gives us 24. And there you go. That's the answer. I like these Riemann sum problems. You know what? Once you get the hang of them, they're almost pretty quick, and they're the kind of problems you'd want. You'd almost think, man, I wish I was having the quiz again, and I had a Riemann sum problem on the quiz, because that would be cool. I'd be able to fly through these. All right, number 10, our last problem for this week. We still get one more quiz. And next week's, there's some great problems on next week's. It's a great quiz. Okay, well, but let's finish this one first. Okay, so we want to use a Riemann sum. Our function here, we have 17 over 1 plus 2 to the 4th. That's an interesting function. And we're going from negative 5 halves to positive 5 halves. All right, that's curious. And we want to have 5 equal parts. And we're going to choose the center on each part. Okay, so we want 5 equal parts. So, let's say, is that 5, 1, 2, 3, 4, 5? Yeah, there we go, 5 equal parts. Now, we've got to think a little bit more. This one's not quite so easy. First off, let's figure out where our cutting points are. In other words, where do we make our partitions? So how far apart is negative 5 halves and positive 5 halves? So if you were to go the whole length here, that would be 5. So I want 5 equal parts. So that says that each individual part is going to have length 1. Okay, so that's easy enough. So that says if you start here, to get to the next dividing line, you would add 1. Negative 5 halves plus 1 gives negative 3 halves. Negative 3 halves plus 1, negative 1 half. Negative 1 half plus 1 is positive a half. 1 half plus 1 is 3 halves. In case you're wondering how am I doing that, whenever I add 1, it's like adding 2 over 2. So it's like adding 2 to the numerator. Now, let's be careful here. Our point is not negative 5 halves or negative 3 halves. It's the middle. So we want the middle between them. So right now we're a little bit nervous because we're like, the middle looks terrible because these are fractions. Let's start with the middle one. What's halfway between negative a half and positive a half? 0. Okay, now to get to the next one, just say, I need to go over by 1. So that'll be 1, 2. Here will be negative 1 and negative 2. So these points, these are where we're going to do the fancy term for it is sampling. Where do we sample our function? In other words, where do we sort of say what's happening to the function at those points? And let's use that to sort of get an estimate for what's happening to the function in general. All right, so we've already pointed out, we'll write down again, that the width is 1. So we can say that, the area is approximately, we're going to have the function at negative 2 times 1 plus the function at -1 times 1, plus the function at 0 times 1, plus the function at 1 times 1, plus the function of 2 times 1. All right, I'm going to stop doing the times 1s because times 1 doesn't change anything. Okay, so let's plug in -2. So we're going to get 17 over 1 plus -2 to the 4th. Well, that'll be -2 times -2 times -2 times -2, which gets us 16. All right, f at -1 is 17 over 1 plus -1 to the 4th is 1. F of 0, 17 over 1 plus 0. F of 1 is 17 over 1 plus 1, because 1 to the 4th is 1. And f of 2 is 17 over 1 plus 2 to the 4th, which is 16. So here we have 17 over 17, which gives us 1. Here, 17 over 2, well, that's 17 over 2. Then there's 17. 17 over 2 again, and here we get 1. Now, notice we have a 17 over 2 and another 17 over 2. If you combine those together, that gets you a 17, right? So 17 and 17, 17 halves plus 17 halves is 17, plus another 17 gets us to 34, 35, 36. Whoops, I forgot my plus sign. 36. So we get that the total is 36. And that's an approximation. Is it a good approximation? It's an okay approximation. It's probably significantly off because, you know, these are big widths. Really, the best approximations come by splitting things into smaller and smaller parts, but that involves a lot of computational work. Now, there are things that love to do computational work, and we call those computers. Computers, by the way, used to just be the people who would be in charge of doing sort of manual computations, additions and subtractions and multiplications. And then, you know, 30, 40 years ago, that started becoming machines taking and doing that work. But yeah, computers, they love doing this kind of work. So thank goodness we have those. All right, well, that's the last problem for this quiz. We get one more, and that's going to be good. So come back, and we'll see you next time. All right, stay healthy, and we'll see you again. Bye.